Hey, Billy C here. We're looking at my non-functional CMOS keyboard, and what we want to do is make it functional. And so what I propose is that we go through each of the sections from start to finish, see what's working, see what's not working, and try and put it in order. Okay, here we are. These are the oscillators. These two friendly fellows. These are CMOS hex inverters. Basically, they're a NOT gate, and they operate with these 12 resistors. These are a kind of multi-turn variable resistor. And multi-turn means that instead of just turning through a few hundred degrees, they actually turn through several circles. Those resistors are helping control the timing that's set up by these capacitors. Barely visible, these little black rectangles. I don't know if you can see them, but there's 6 of these per chip, and that makes 12 oscillators between these two chips, and those 12 oscillators generate the 12 notes of a chromatic scale. So those are NOT gates. I'm going to try and do a quick explanation of what the NOT gates are doing. Here we go. Let's see. Draw a little NOT gate. This bubble means NOT, kind of. There's the input, there's the output. And what happens with the NOT gate is if you give it a signal, let's say in this case a 0, it gives you the NOT signal, which would be a 1. The digital logic we're working with. And that's what it does. If you give it a 1, it'll give you not a 1, which is a 0. Now what happens if you connect these two together? When this is 1, it flips back here really quick and makes this 1 presents itself here, comes through and becomes a 0, which becomes a 1, which becomes a 0, which becomes a 1. In other words, we'll disregard these. If you put a 1 here, you get a 0 here, which comes back here, comes through and becomes a 1, which goes back through here, goes through, becomes a 0, and so forth, and you get a steady streams of 1s and 0s. It looks kind of like this. Now, if you put a capacitor here, let's draw the capacitor right through our 1s and 0s, and connect it to ground. And if you use a resistor up here to control the discharge time of this capacitor, and if you make this a variable resistor, now you can change the speed of this pulse train by varying the time it takes for this capacitor to charge and discharge, and change the input, and then start the feedback loop. So you get something that you can change the speed of. Ooh, that's hard. And that's basically what I'm doing with these 12 outputs on those two circuits, or on those two integrated circuits. And what we want to do next is see if we're getting any sound there out of those outputs. So I'm going to test with this little probe here. And I do hear something. Let's some volume. Woo, too much volume. I'm going to test with this little probe here. Let's see what we get. Excellent. That's one. That's another one. Those are all working. And on the other side, well, let's just do these. Excellent. Awesome. That's going to be a short circuit. Doesn't sound good. There we go. Excellent. Awesome. Tight here. All right, that's 12. That's the top octave, and I'm pleased because that means the first section is all working. That means I'm getting all 12 notes. And so next we'll look at the divider section, which is going to be hard to look at, isn't it? All right, dividers next. Okay, and now we're talking about the dividers. For dividers, I'm using the CD4520 dual, you can call it a binary counter, any number of things. That's these. There's 3 of them here, and underneath the rest of the spaghetti junction are these 3. And the notes from these 2 go to these 2. Now there's 12 notes coming from here, but you only see 6 of these. Well, they're dual, so there's actually two circuits on a chip here. So the 4520 is a dual divider. So what's happening, we'll go back to our diagram. You'll see we are taking the signal from the oscillators and we're sending it to the clock on the divider. And then what happens is it divides that clock signal by these numbers, 2, 4, 8, or 16. It's a binary divider. Okay, so what that means is when you divide this pulse train here by 2, what you're going to get is a pulse train that looks like this now. It's going to look the same, but you're going to notice that the periods of being high or low are twice as long now. So it goes twice as slow. So in other words, divided by 2. And then this one, the pulse train for the divide by 4 output is going to look like this. I'm going to go with some instant propagation delay here in just a bit, and I think we're going to get good propagation delay out of the circuit. But now you can see that this one is twice as long as that. It goes 4 times as long as this, so it's slower yet. And what that means in musical terms is this is an octave lower than that, and this is an octave lower than this. And you know, the output for the divided by 8 looks something like this, and the output for the divide by 16 is going to look like that. Blah, 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 blah. I'm not going to draw the whole thing in because I'm getting ink all over the bottom of my hand. But that's what comes out of dividers. And the dividers, in that way, divide each of the 12 notes by 4 different octaves, and that gives you 48 notes. So the 48 notes come off of these 6 circuits. They're referred to as the dividers. Let's see if we're getting any notes. Well, there's 4 octaves of something. 4 more. Excellent. Oh yeah, there they are. Excellent. That's half of them. There we are. Those are all working. One more to go here. Oops. That's all of them. Sounds a little sketchy because I'm just kind of flailing around. But the good news is they all work. So, with that, we'll move on to the switches, or the so-called AND gates. Okay, so I had to move things around and work things out, and I wanted to explain about AND gates. And I tried. I did a few shots, and it just got worse and worse. So I decided to come up with a visual aid. So these are the AND gates. These are the oscillators, and these are the dividers. I've represented those by an oscillator, a divider, and an AND gate. Now let's look at those a little more closely. Yeah, move back just a bit. Okay. So again, this is the oscillator. I'm using the same components. The 4106. This is a multi-turn trim capacitor, just like that. And this is a resistor. This is a little bit bigger than the one I'm using, but I wanted to slow everything down. This is a capacitor. I'm sorry. This green thing is a capacitor. It's 0.1 microfarads, and I'm using it to send a fairly slow clock signal to the divider. And then the dividers, there's 4 of them, well there's 2 of them on this package, but there's 4 divisions on this side, 2, 4, 8, and 16. We'll put it on 8. And then it cruises over here to the AND gate. And there's an input, and then there's this resistor here that's holding the other input low, and then this is the output, and it's going to this LED right here. So let me throw the switch. Poof. And this wire is the same. This represents the keyboard. It's just like the same as this wire here that connects to positive, and here it connects to positive. And when I, oops, now it's disconnected from everything. And when I put it here on this input, I don't know if you can see that, but the light starts blinking. Wow, it's so barely visible, but it is blinking. Maybe I can kill some. Hey, look at my forehead. I don't know if you can see that, but I turned out the lights a bit, and you can see, hopefully, that it's blinking. And that's blinking at the lowest octave here. I can make it blink twice as fast, and then twice as fast still. And now you can barely even see that it's blinking. It's kind of like wavering, and now it's even fast. Yeah, now it's as fast as it'll go at that note. And actually, you can see on the screen it is kind of flashing there. I can't see it in real life. It just kind of looks dim. There we go, but there we go. It's blinking again. Now I'm going to switch this out to the capacitor I use in circuit, if I can find it. There it is. This is a 0.015 microfarad capacitor. It's a lower capacity capacitor, and those are the ones I use for the notes. So let's take a listen. Oops. So you see I got 4 octaves. There's a 5th octave too. That's the input here on the clock. Which doesn't give me much. You know, I mean, you can do better with a bugle. But I have, I have a whole dozen of these, well, nearly a dozen. I have 11 of those, and with each one of them putting out 4 notes, I get 44 notes, which, ta-da, let me lift this up until it hits the light up there. You can't quite count it, but there's 44. I'm literally holding the tripod here, so some pretty clever film work. It's actually a bipod because one of them's hanging from the ceiling. Anyway, that's how the AND gates work. You push the key, or you don't. See how the light goes out? No more note. Push the key, electricity flows through this wire, into the keyboard, out through all this bunch of wires, into the AND gates, and out to the speaker. But that is where the problem is. There's something going on the back of this board, and it's bad soldering. So I'm going to go back and solder all this together, and we're going to go through that together. But first, we're going to talk about what is all this other stuff. So give me just a few minutes, and we'll look at some of these other stuffs. This is the rest of the stuff. One of the stuffs is this thing. This is the master tune. Let me just bring a note in, and this will tune it. And check it out. Pretty sweet. So it's not really for that wide of a range, but it'll push you a few cents either direction. So there's that, and then there's this part, which is the interface for the sequencer. And what it has is a bunch of holes on this thing that's kind of arranged like 1 octave of a piano keyboard, and that's what it represents. You go up the scale. You get 4 octaves because I just told you about the 4 octaves, right? It's just like an output of one of those divider chips, but out to here. So that's really what it is. These are the outputs for the dividers, and they're just all right here. And these are the notes that they represent. And not only do you get the 4 octaves, but you get 4 octaves again in case you want to use a note over again. And then the other holes on the bottom I use as multiples. So if you need a bunch of C's, you can pull the C and E down to here, and you get 5 more because these are all tied together. So you use one hole to tie them together to a note, and the other 5 are tied to the 6th. And you can even take a note and jump it over here. Say you have a song that's in some key that doesn't really use C sharp very much. You can tie your multiple over to C sharp. These guys that you can't see well are 4 groups of 4 inputs. They're not very easy to see. But those represent 16th notes, say in a 4/4 rhythm. You can you can use them differently, but that's kind of the most common way to use these things. So you take whatever note, say you want to put the and of 3, which would be right here, and you want it to play an F, you put it right here, and that's what's going to happen as it cycles through. That's really the best thing. This is the computer of the whole bit. This is the brains of the sequencer. It's not much. It's a 4067, 1 of 16 switch, and it just cycles through. It's 16 switches in any order really that you want it to, if you do some clever logical input on these 4 inputs, which are the they're called A, B, C, and D inputs. They're weighted binary inputs, which is a bit of a jargon thing, but we'll get into that when we start talking about the sequencer. And so that's about it. That's the full feature of this device. You have a keyboard that plays 44-note polyphony. You got a master tuning system in case you're a little bit out of tune, and also you can wonk it way over here and totally blow the tuning system out of proportion, and it just does weird things. You got oscillators, dividers, and switches, which are or the AND gates. And then over here is the oh, we can't see it. Over here is the sort of analog interface, which I think is another trouble spot. I'd like to make an analog and digital interface, which I think is going to require a bunch of diodes. So that's where I'm going to be working. I'm going to be working on this stuff, but I think the next demonstration is going to be the sequencer. But yeah, sequencer, next video. Hellfire, this has been Billy C.